Okay, section 4.2, mean value theorem for derivatives. I guess buffalo are mean. Not quite sure where the picture came from. All right, so the mean value theorem for derivatives says that if you have a differentiable function, f of x, over a closed interval, then at some point between a and b, the this is the formula for the average slope, the slope between 2 points. So the average slope has to equal the derivative at some point between a and b. So here it is in kind of plain. Well, first of all, differentiable implies the function's also continuous, because remember, if the function's differentiable, it has to be continuous and smooth. So the mean value theorem only applies over a closed interval. So it has to be a closed interval in order to apply this. So what the mean value theorem says, kind of in plain English, is at some point in that closed interval, so there has to be some place in between a and b, where the actual slope equals the average slope. Or say we were thinking of velocity, where the instantaneous velocity would have to equal the average velocity. So that's what the mean value theorem is stating. So suppose here we have a function. So here's a function f of x. And here's a point A and a point B. So if you were to calculate the slope between A and B, you would just take the function value evaluated at B minus the function value. So like the change in y over change in x is what we're looking at there. And that gives you the average slope. If you look at the tangent that's parallel, what this is saying, the mean value theorem is saying there has to be some point in between A and B where this average, where the instantaneous slope is equal to the average slope. A couple of somewhat obvious definitions. A function is increasing over an interval if the derivative is always positive. Now, we've talked about that quite a bit, that you would have, if the derivative is positive, that means the slope is positive, which would indicate that the function was increasing over that interval. And if the derivative is negative, that indicates the slope is negative, so that means the function would be decreasing over that interval. So, for example, if we were to take a look at, well, I guess this isn't an example, but I'm going to be showing you some examples, by the way. So if we were to take a look at two functions and say that these two functions have the same slope at any value of x. So if we could take one, and this program won't allow me to do it on PowerPoint, but if I took one of these curves, I could drag it and make it match up the other one. So these are functions with the same derivative, but the functions just differ by a constant. So for an example, so say you want to find the function f of x whose derivative is sine x and whose graph passes through 0, 2. So think about the function whose derivative is sine x. So now we're going to go backwards. We know that the derivative of cosine is negative sine. So that would mean that the derivative of negative cosine x must be equal to sine x. So the function we're looking for is negative cosine x. Now we want to force that graph of negative cosine x to go through the point 0, 2. So we don't know what that constant, without that value 0, 2, we don't know what that constant would be. Okay, so we know that it's negative cosine x plus some constant. But now we can use that 0, 2, and we can substitute in 0 for x and plug in a 2 for f of x. So you get this equation right here that you want to solve. And when you solve that, cosine of 0 is 1. So you get 2 equals negative 1 plus c. And you solve for c, and you get 3. So by knowing this point, we had to be given this initial value. And by knowing the initial value, now we can substitute that initial value into our function, and we can actually find out what that constant is. So now we know that the function in question is negative cosine x plus 3. But we had to know that initial value in order to determine the value of c. All right, this process of finding the original function from the derivative has a name, and we've talked about it actually in class already. It's come up. It's called the antiderivative, and typically we use a capital F to represent that antiderivative, and the process of finding an antiderivative is called antidifferentiation. So anyway, so that is an antiderivative, which we've kind of talked about already. We'll do some more examples. And we will actually be doing a lot when we do integrals, which comes up in chapter 5. All right, so here's another example. Find the velocity and position equations for a downward acceleration of 9.8 meters per second squared and an initial velocity of 1 meter per second downward. Now, the downward tells us that it's going to be negative, so it kind of gives us our direction. So we start with our acceleration, we have is 9.8. Since acceleration is the derivative of velocity, then velocity must be the antiderivative of acceleration. So we're just taking the process and going the other way. So that means if we think about like the power rule in reverse, when we're going through and when we calculated derivatives, now we're going backwards. So the velocity would have to be 9.8 times t, because we're dealing with respect to time, plus some constant that we don't know. However, we're given that there's an initial velocity of 1 meter per second. So that means that when t equals 0, we can now solve for our constant. So when we do that, we get c equals 1. So this becomes our equation for our velocity. Since the velocity is the derivative of position, position must be the antiderivative of velocity. So we could actually back it up a step further and find out what the position function would be if we calculate the antiderivative of velocity. So we're doing the power rule in reverse. And what you do is you're going to increase the exponent by 1. Remember, before we subtracted it. Now we're going to add 1 to the exponent. And then we have to multiply by the reciprocal of whatever the new exponent was. Remember, and you can kind of double check this easy enough. If you did the power rule on this, you would multiply this. Oops, where did it go? If you do the power rule on this, you would be multiplying the 2. You'd be bringing the 2 down, multiplying by 2, and the 2's would cancel. So, that makes sense. When you think about it, you can kind of see how that would work. Plus t, because we're going to have, it was plus 1, so plus t, plus a constant. So that's our position function. And you can always double check. Take the derivative of your position function, and you should get back to what your velocity was. So it's easy to double check that. All right, so we have, since the initial position is 0 at time 0, then we can plug in a t equals 0 and find out what our constant was, which would be 0. So now we know that the position function is 4.9 t squared plus t. And that's your process for antidifferentiation. Okay, I'm going to be doing some examples, so I'll try and get those uploaded soon.